Hi, my name is Matthew Park, and I'm happy to introduce you to my video project for structural analysis. Firstly, I'd like to introduce you to my structure. It's an outdoor dining table, and I chose it because the supports weren't located at the end of the table. And whilst this is a minimal deciding factor, I thought it was going to be a challenge, but I'd like to overcome it. So this is the basic force diagram I've constructed, basically illustrating that the distributed load has a 9.99 kilonewton meter force acting on the right side of the structure. And this made things difficult as I had to divide the structure into 3 different sections, basically like this, which I'd never done before. But I wanted to take on the challenge and see how I'd go. So moving on to the first step by calculating the forces acting at the supports. I took the moment around A, this point here, to calculate the force at BY, which turned out to be 9.419, and AY 2.568, which made sense as there was more of a load acting on the right side. Okay, moving on to this first part. In order to calculate the equation for the shear force diagram, I had to take, I made X go from this way, and as you can see, Bx equals is going down. So basically, this is a bit confusing down here, so I'll quickly rewrite it. Sorry. So negative Vx minus, it turned out to be 2.08125x squared. And once you flip over the Vx, it turned out to be this part here. And that turned out to be a negative parabola. And as you'll see when we later go to the shear force diagram. And for the moment, bending moment diagram, it's essentially the same thing except with moment. And the formula here had three x's. So it turned out to be a negative 0.69375 x cubed, with this being the formula for the triangle and the distributed load. And this is basically just for the other parts. Whilst this was a challenge, I felt like once I got past the first part, I felt like I gained more knowledge on how to do it, and this got a bit easier. As you can see, the shear force diagram and bending moment diagram kind of looked like that. It looked a bit odd, but I cross-referenced it, and it looked okay in the end. And as you can see, the bending moment diagram had a maximum as well as a minimum. So there would be 2 maximum bending stresses, both compressive and tensile. Moving on, maximum shear stress is calculated using this formula. So first I had to calculate the moment of inertia, which is done using this formula. The base being this part and height being this. The area, so since we were calculating the max shear stress, I chose to put the P in the middle. So basically I've done that because that would calculate the partial area to be a maximum. If the P was located, say, up here, the area would not be at a maximum. So basically when dealing with rectangles, you need to put the P in the middle to create a maximum area. By getting this, the vertical shear force from here, the maximum. I just subbed it into the equation to get a result of 0.2472 MPa, the maximum shear force, which was located at B, which is located here. Maximum bending stress, I had to do two calculations as I had both a maximum and a minimum. Formula is here. Theta equals negative my over I, with the negative representing the compressive sector. The tensile bending stress was the maximum of the bending moment diagram, so that was located here, the maximum. Y equals 7.5, and we had to convert the moment of inertia to meters, so that ended up having a negative 10 to the negative 7. Putting this into the formula, we received a result of 2.06 MPa. Basically the same thing with the compressive bending stress, except there was a negative at the start. So I got a result of negative 3.87 MPa for the compressive bending stress. The main issue I had here at the start was converting units. Converting the moment of inertia to meters instead of millimeters. I had to do that a couple of times, as well as doing this. So by calculating this on the calculator, you got a result something like 2063, which I didn't really know how I was getting that, but then you had to move the decimal places 3 spots like that due to the unit change. Moving on to stress transformations, maximal principal stresses. We were told to calculate the principal stresses. We had to make theta y and the shear stress equal to 0. By doing this, by inputting these values into the formula, we negated this, making it equal just to 2.06, and same with here, getting rid of this also, which gave us this value, and basically gave us theta 1 equals 2.06 MPa, theta 2 equals 0. Also with this, we were told to make all thetas equal to 0 to calculate the maximum in-plane shear stress. And the formula for that is here. So making this equal to 0 negates this whole section, basically making the maximum in-plane shear stress equal to that, plus minus, which is here. So you get a result of plus minus 0.2472 MPa. Just quickly going to failure planes. This formula here makes us negate this as well. So it gives us a result of 0. Therefore, by default, 2 theta s equals 0, or 2 theta s equals 180, and therefore theta s equals 0 degrees, or theta s equals 90 degrees. So basically got those values. And just from an overall standpoint, maximum tensile bending stress was located at this point. Maximum compressive bending stress was located here, and the maximum shear stress was located at B as well. So B undergoing a lot of stress there due to the distributed load acting like so, which made a lot of sense. So finally, just like to thank you for listening to my video project. Basically, I found this very beneficial. I felt like I was problem solving a lot more than I usually would by doing this individually rather than a group. If I didn't know something, I'd have to look it up myself and overcome the issues and problems that I came across. So yeah, I found this very beneficial, and yeah, learnt a lot from this task. So yeah, thank you very much for listening. Yeah, my name is Matthew Park, and hope you enjoyed.